Alrighty, let us start this video. I want to do a little bit of an exam review for our first test. This test, of course, is going to cover all the topics we've done in thermodynamics. So, what did we go over? What were the big topics that we discussed for this particular class in thermodynamics? Of course, this topic is a whole field in physics, and so we can't cover everything. This is kind of an introduction, basic overview of some of the important topics. You would have seen some of it in chemistry. You'll probably see more of it in chemistry classes. And if you pursue physics, then obviously you will get more in-depth, more classes that are dealing particularly just with this subject, statistical mechanics and things like this. But for us, what did we do? First big thing, calorimetry. So calorimetry, what was this? These were the types of questions where you had some system. We would assume the system is close to the environment, so maybe you have some hot water in a container. We assume that the heat from that hot water can't escape into the atmosphere and be lost. Of course, in reality, that's not how things work. You have to have special equipment, a calorimeter, or some kind of insulated vessel to allow for this, but right now we're just kind of doing the theory, and then in practice you have to modify things to account for some of these idealistic situations not actually being true. So we have a system close to its environment, and maybe we have multiple different substances that are, maybe they start at different temperatures, we combine them all together, mix them all up, and then wait a while, and eventually all the temperatures seem to equalize where everything comes to some same final temperature. And we may want to answer questions about the system. Maybe I have some hot coffee. How much cold milk should I add in order to bring down the temperature of the coffee to 80 degrees Celsius? Or I added this much ice to this particular hot soup. What will be the final temperature? Or how much ice should I add? All these types of things. These were your basic calorimetry type problems. What we found was basically we use conservation of energy to solve them. We say the heat, Q of course being heat, gained by one object, plus the heat gained or lost by the other object, and then however many objects there are in the system, we add up all the heats, and that is, some of them are positive because they're gaining the heat energy, some of them are negative because they lose heat energy. You add all these changes up, and it better be equal to 0. Why? Because energy is conserved. If I have some hot coffee, it loses 1,000 joules of energy to some cold milk. Well, the cold milk better gain that 1,000 joules of energy. You don't just gain part of it and the rest just disappears out of nowhere. Nor vice versa. You can't put maybe some ice cubes in a room temperature liquid and then expect to be able to necessarily melt all the ice, because there might not be enough heat in the room temperature liquid to be able to melt all the ice. So you can't gain a bunch of heat energy out of nowhere either. It must have come from somewhere. And so another way you can see it is to think of it as Q gained is equal to Q lost. All the things that gain energy are over here, all the things that lose energy is over here. The problem with doing it this way, which is why I don't say it this way, is because there's a hidden negative sign over here in Q lost. These things have lost energy because their final temperature is lower than their initial temperature, and we'll see when we do the equation where a negative sign comes into play for that. But you have to change the negative sign when you put it on the other side of this equation, and so it's kind of hidden in the delta t term. That delta t is actually initial minus final rather than the standard final minus initial. So while this particular way of writing the equation is logical and it makes intuitive sense, this first way is the way I always go about teaching it, because you don't have to worry about negatives versus positives. They all come out purely by the mathematics itself. You don't have to think about it. All right, so that's the basic overview, but of course, generally speaking, for some system, I got hot coffee and some cold milk I'm sticking in there, I don't necessarily know how much energy is going to change, how much energy the coffee will lose or the milk will gain. I have no idea what these numbers are, so I better have some way of figuring them out so I can stick them into this equation. And that's where we have two basic big-time equations for this particular section. The first one is Q is equal to Cm delta T, where, of course, Q is heat, C was specific heat. Specific heat, if you remember, was basically telling you what type of material are we talking about. Different materials will take different amount of heat energy in order to change their temperature. So maybe, aluminum, you may be able to heat it up really easily by just adding a little bit of heat energy to it. Whereas maybe a block of wood, in order to get its temperature to raise the same amount, you may have to add a heck of a lot more heat. So different materials have different specific heats. These things are basically just telling you it's going to take 500 joules of energy per kilogram to raise the temperature of this object by a degree. This other one, maybe it takes 4,100 joules of energy per kilogram in order to raise its temperature by 1 degree. M was mass, of course. You have more of an object, it's going to take more heat to raise its temperature. And then, of course, delta T, that's your final minus initial temperature. And for all of our equations in physics, we're always going to use Kelvin as the unit of temperature, where Kelvin temperature is just Celsius temperature plus 273. Okay? Don't worry about the decimal, we're just approximating here. Now, for the particular case, the special case, where our equation has delta T in it, so we're subtracting two temperatures, finding the difference in temperatures, then it turns out that you can either use Kelvin or Celsius. So if you happen to be doing a calorimetry problem and you're given the temperatures in Celsius, number one, you should convert to Kelvin. Okay, just to be appropriate, just to be safe, because there will be equations where you do have to definitely convert. Or, because this equation only needs delta T, you can go ahead and leave it in Celsius and you're fine. Okay. So, this equation for Q, you use anytime the particular substance you're talking about is not changing phase. So you just have some hot water and you're going to cool it down to some new temperature. Or you have some cold milk, you're going to heat it up to some new temperature. But the whole time it's not going to melt or boil or anything like that. You're just changing the temperature. Then Q is Cm delta T. However, if you are going to change the phase in the process of doing whatever we're doing with these systems, like for instance, I have some hot coffee and I put a couple of cubes of ice in the hot coffee to cool it down. Well, those cubes of ice not only will take away energy to heat up to some new temperature, but they will also take away energy only just to melt, even without changing temperature. And so to figure out how much energy that part uses, that Q is equal to M times L, where L is called the latent heat. And this is basically kind of like specific heat. It depends on the material. But it just says, if you have a kilogram of ice, it's going to take 334,000 joules of energy to melt that ice. Now, the whole time it's melting, it's not heating up, it's not getting warmer, it's still at 0 degrees. But it is still soaking in energy. Or vice versa. If you have some boiling water and you condense it, boiling water, the steam, you condense the steam into water, you again are going to be giving away energy purely by changing the phase of the water from steam into liquid water. And so with these two equations, any particular problem you may have in calorimetry, you basically get down to something like this. Let's say we have the example, you have some hot coffee in an aluminum cup, and you put some ice in that cup to try to cool down the coffee, and you want to know what's going to be the final temperature of the system. Well, what you would do is you'd say, okay, I have some amount of Q for the coffee, because the coffee's going to cool down. The cup that it's in is made of metal, so that, of course, if we actually had some hot coffee in a metal cup, if you try to pick up that cup, it's going to burn your hand because the cup is hot too. So as the coffee cools down, so will the cup. So you have Q for the cup. Then you have the ice. You stick the ice in there, so there's going to be some Q for the ice. However, this particular piece is one of a series of steps that the ice is going to undergo. The first step is you have to warm this ice up to get it to its melting point. Because ice can't melt unless it's at 0 degrees. Well, if the ice started at -5, you first have to warm it from -5 up to 0 before it can even start to melt. So that's what this piece is. Then you have a piece, and I call it Q melt. This is once you've gotten the ice to 0 degrees, how much energy is it going to take or lose, whatever, to melt all of that ice. That's your ML term. Then you have a term, now that you've melted all of this ice, it's still at 0 degrees, so it's not at the final temperature yet. However, now it's liquid water. So you need another Q to now warm up that melted ice to its final temperature. So notice, these are 3 terms all having to do with the amount of ice you stuck into that cup. The coffee is its own thing, the cup is its own thing, the ice is its own thing, but the ice, because it's going to go do a phase change, has multiple steps. One step to warm it up so it can melt. The next step is to actually melt it. The last step is, now that you've melted it, heat it up to its final temperature. And in all of these, except for the melt term, they all have Cm delta T. Delta T is final minus initial. The only thing to watch out for is for the ice here, his final minus initial, his final is 0 Celsius. Not the same final temperature as everything else. And the reason is because the ice can't get to that warm final temperature. The hottest you could possibly get the ice is 0. So his final temperature is 0. Now once it's melted, and we're on Q melted, he's starting at 0, but his final temperature can be whatever it needs to be, up to 100 degrees, of course, before it starts to boil. So usually everything will have the same final temperature, unless we have little weird hiccups like this where you're melting the ice, so the ice can't get to this final temperature until after it's melted. But this is calorimetry. This is how you're going to go about doing it. Do you have things that change phase? Do you not? You stick it all in this equation, set it equal to 0, and you're going to solve for whatever your unknown is. All right, once we did that, we started talking about heat transfer methods. And we talked about how there's 3 that we know about: conduction, convection, and radiation. But we really only mathematically worked with 2 of them. Conduction, that was transferring heat by actual physical contact between the molecules. And we said that the heat transfer rate, that is how much energy per second will flow through your system by conduction, is given by something called the conductivity. So again, this is one of those things that has to do with the actual material. Maybe fiberglass has a certain conductivity, and glass has a different conductivity, and drywall has a different conductivity, and aluminum something else. And depending on the material, either it allows heat to transfer through it quickly, or it makes it go much slower. That's kind of what conductivity is going to tell us. It's just a number that has to do with the material. What else should this depend on? Well, of course, if you have a very big object, then there's a lot more surface for contact, and so there's a lot more places where the heat energy can either come in or out. So certainly the speed, the rate at which this heat is transferring through the material should be proportional to how big the object is. A bigger window will allow more heat into your house than a smaller window will. And so it should depend on the area of the material we're talking about. It should also depend, of course, on the difference in temperatures between the two objects that this conduction is happening. So maybe you have your hand and a stovetop, and you put your hand on the stovetop. The stove is going to transfer a whole bunch of heat energy into your fingers. It's going to burn you. Well, if the stove is off, and so it's just at room temperature, and you put your hand on it, well, there's not going to be a lot of heat transferred there. But if the stove is on and is really hot, you're going to have a heck of a lot of energy transferring into your hand. So, of course, the difference in temperatures should make a difference in how fast heat transfers into the objects or through the object. And then it should also depend on the thickness. If you have a super thick bulletproof glass window, then it takes a long time for heat to try to get through all of that material. Whereas if you have a thin piece of aluminum foil, that heat can get through that aluminum foil really, really quickly. And so it should also depend on the thickness. Unfortunately, L stands for thickness here. So if we're talking about, some wall and a window or whatever, and heat is trying to transfer through this system, well, this thing is at some temperature T1 on the left, the other side of the other object's at some T2, there's some area of these objects, the conductivity 1, conductivity 2, this is the thickness of the first material, this is the thickness of the second material. And so we would use this equation to try to figure out whatever it is we need. Or you could have, the rods, cylindrical rods like this, maybe a silver rod touching up against a gold rod. Now you see why thickness is called L, because it's the length of the rods here. And the area has to do with the area of the opening, the ends, the pi r squared stuff. And so that's conduction. The amount of heat per second that travels through a system by conduction is given by this equation. Now, if we put two materials together, like in these two situations here, then we have to use a little bit of intuition to figure out how to solve it. Because you say, well, wait, how do I figure out? I've got two different Ks, I've got two different Ls, two different temperatures, but only have one equation sitting here. What do? You use this fact from physics. You say, well, if I've got this combination of materials, this layered system, and I'm going to try to send energy through that system, well, some of the layers are really slow, other layers are really fast. So how is the energy going to flow through the system as a whole? Well, it turns out that those slow layers are going to cause traffic jams in the fast layers in such a way that the amount of energy that flows through this first layer per second is the same as what flows through the second layer per second. So even though each individual layer, if they were just by themselves, one may be let 10 joules per second, the other one only 5, when I stick them together, there's some kind of a combination effect. The slower thing is going to slow down the faster thing, and so the whole thing gets some new heat transfer rate, maybe, 7 joules per second, whatever. Such that the first layer has the exact same number, Q over T, as the second layer. So we would say Q over T for the first layer is equal to Q over T for the second layer. Why do we want to do that? Well, the reason is because if I want to know Q over T for the whole system, I only need to know what is Q over T for one of the layers, since they have the same Q over T for each layer. So if I just look at this right here, in fact, let me do it in a different color. If I look only at this layer, and I say, okay, let me just find Q over T for that, and I got my problem solved. Who cares about the second layer? We run into a problem, because we'll see Q over T, 1 is K1 A1 over L1 times delta T1, which is his difference in temperatures on either side of his object. Well, on the left side it's T1, that's fine, but the right side is not T2. That's on the other object. The right side of this layer has some unknown temperature right there. We'll call it T3. Now, if you told me what that T3 was, then I could go ahead and solve this because I have all the other numbers. But since I don't know what T3 is, in order to solve this problem, I got to figure out what that number is. That's why we use this, because we'll say all of that stuff, the green stuff, must be equal to the red stuff. K2 A2 over L2 times his left minus right temperatures, which would be T3 minus T2. And now you see we have this green equals this red. Everything I know all the K's, I know all the A's, I know all the L's, I know T1, I know T2. The only thing I don't know is this T3. And so I just have an equation to solve for T3. I get my T3, some number, it better be between T1 and T2. But now that I have it, now I can choose. Do I want to look at the green layer or do I want to look at the red layer? It doesn't matter which I choose, I'll get the same answer. Pick one. Let's say I pick the green layer. Well, now that I know my T3, that number gets put in there, and now I just have a bunch of numbers I could solve the equation. So that's conduction. If I have 3 layers instead of 2, then Q over T1 is equal to Q over T2 is equal to Q over T3. I'm going to have a T3 and a T4, 2 unknown middle temperatures. So it's just more tedious, more algebra, because now I'm going to have 2 equations, 2 unknowns type thing. But once I get those T3 and T4, I just stick it into one of the layers and I got my answer. The other one, radiation, this 2 is an equation that has to do with the heat transfer rate, so how much heat will flow per second, but this time due to radiation. And what is radiation? Well, just as a quick review, you have a nucleus, and then you have some electrons in these orbitals. Of course, this isn't how things really work, but this is a good model to help us have the intuition of what's happening. And in these orbits, we have some electrons, and each electron has a certain amount of energy, which is based on what orbit it's in. Of course, the lower the orbit, the closer to ground state, the lower their energy. You give them a little bit too much energy, they get excited, they jump up to a higher orbit. So, if you've heated up some material, some metal or something, what you're doing is you're giving a bunch of extra kinetic energy into these molecules. And into the molecules means into the electrons and all sorts of stuff. So you're vibrating these molecules, gives a bunch of energy to the electrons. So maybe one electron, let's say this one here, gets so excited he jumps up and goes into this orbit here. And in order to do it, the reason he did it was because he gained a bunch of excess heat energy from some source. Maybe you heated it up. Maybe this is a piece of charcoal and you lit a fire on it and it starts to glow red. So one of these electrons gained a bunch of energy from the fire, went up to this higher energy level. Fine. No big deal. It's still the same molecule, still the same atom here. All you did was move an electron into a higher energy state. It didn't change anything. However, nature doesn't like being in an excited state. It always wants to get down to the lowest energy state possible. So this electron is going to say, you know, I don't like being here. I want to go back to my home. I want to get back down to the lower energy state. So it's going to say, come back down. I'm now back in my home. But In order to do that, it had to get rid of all that extra energy it had, which made it get into this higher orbit in the first place. That's why it was there. It had too much energy. So it had to get rid of this energy so it could go back home. And the way it gets rid of it is it shoots out some photons, shoots out some light. And so that's why when you heat up charcoal or you heat up a pan really, really hot, it starts to glow red. What's happening is, as something is heated up, it's always glowing, whether our eyeballs can see it or not. It's sending out all this energy all the time. But if it's so hot that this excess energy that it's giving off, trying to get back to the ground state, has a frequency or an energy that's high enough to make the light visible light, then we see it start to glow. And that's why as you continue to heat something, it starts at deep dark red, gets to orange and then yellow, and eventually white. That's because as you give it more and more energy, the light it has to give away in order to get back down to a lower energy has a higher frequency, which means more blue, more white. Lower frequency is more red. So that's what's happening. That's how this heat transfer is happening by radiation. It's literally the electrons shaving off a bunch of its excess energy by sending out a bunch of light all over the place that we can see. Or we can't see, depending on the frequency. So how much energy per second is being let off by radiation? That's given by an equation. First, we have sigma. This is what's called Stefan-Boltzmann's constant. Boltzmann constant. And I believe it's 5.67 times 10 to the minus 8. So just a constant. It'll be on the test. You don't have to memorize it. Then it should depend on kind of the material in a way. And the way this one is dependent on the material is by how well does this thing emit the light? How well does it radiate light? If it's perfect, if it's an ideal perfect radiator, we say this epsilon is 100%, so that would be 1. If it's not so good at radiating, maybe it only radiates at a 65% efficiency kind of a thing, then it'd be 0.65. This is a percentage. All right, so that's kind of having to do with constants and materials, fine. What else does it depend on? Well, obviously, if you have a very large object, then you have lots of different places for this light to be emitted from, right? If you have a big, huge sphere, like this, here's my sphere, then all of the sphere are little locations where light beams can be coming out of. Or if you have a little bitty sphere, well, there's not so many places where light can come out. So the amount of heat you get per second should depend on the size of the object in some way, but should it depend on the volume, the shape? What should it depend on? It should depend on the surface. The more surface there is, the more places light can come out. So it depends on A, the surface area of the object. Then, it's going to depend on the temperature. Obviously, I already said that. As you heat up a metal pan, it starts to glow red, and then orange, and then yellow. The more towards blue, the more energy per second is given off, and the more towards red, the less energy is given off. But how does it depend on the temperature? It turns out it depends on T to the 4th. I'll call this T of the object. So to the 4th power. So if you double the temperature of the object, the amount of heat coming out by radiation will go as T to the 4th. That's 16 times more energy. But it also should depend on what's its environment. Just like with conduction, if your hand and the object you're holding are at the same temperature, then we don't have energy transfer. But if you're holding a snowball in the winter, then that snowball is sucking a bunch of energy out of your hand and making your hand feel really cold. Well, same thing here. If I have a hot object that's in a hot room, well, there's no energy that's going to be transferred because the hot room's going to heat the thing back up immediately. You're not going to lose any energy. However, if it's in a cold room or the vacuum of space or something, then all that energy can come out freely. So it also depends on temperature of the environment to the fourth power. Now, note, this is not delta T to the fourth power. It's not that. That would be T object minus T environment to the fourth. That's not what this is. If it were, then I could use Celsius. I could say the temperature of the object in Celsius minus the temperature of the environment in Celsius, and then I take the fourth power. Unfortunately, it's the temperature to the fourth power minus the temperature to the fourth power. So I do have to convert. Must use Kelvin. Which makes sense. Let's say the environment's at 0 degrees. It's at, actual absolute 0 Kelvin. If I use Celsius here, and let's say my object is at the freezing point of water, it's at 0 degrees Celsius, then I would have Q over T as 0. Because 0 to the fourth is 0, and 0 times all this stuff is 0. But 0 Celsius is 273 Kelvin. So if I convert to Kelvin, well, it's 273 to the fourth power. This is a big number. So in Celsius it's 0, in Kelvin it's some huge number. Obviously the answers don't match, so what we need is the Kelvin stuff. But that's radiation. If you have conduction, then this is the equation you use. If it's by radiation, it's the T to the fourth equation. And then for both of these, if I don't ask for the heat transfer rate, maybe I say, how much energy will this thing give off in 2 hours? Well, all you have to do is multiply the little t to the other side, and you have the amount of heat is equal to blah, blah, blah times the time we're talking about. Okay? Remember, time is in seconds. All right, last topic was ideal gas law. So here, definitely chemistry-like stuff. We have PV equals nRT, or PV equals nKT, depending on if we're talking about moles or molecules. If the problem tells you about the number of moles in this gas and you want to know the temperature, then you use nRT. If instead it says you have 5 times 10 to the 24 molecules of oxygen gas, then you would use nKT, where R is some constant, 8.314, and K is Boltzmann's constant, 1.3 times 10 to the minus 23, or something like that. P, of course, is pressure. Units of pressure are pascals. V was volume. Volume is in cubic meters. And here, because this is the absolute temperature, there's no delta T, no change in T. Here we have to use Kelvin again. Things to note. 1 atmosphere of pressure is 1.01 times 10 to the 5th pascals. 1 liter in volume is 1 over 1,000 cubic meters. And to convert moles to molecules, 1 mole of a gas is Avogadro's number of molecules, which is 6.022 times 10 to the 23rd molecules. So that's a lot. But a mole is, it's just like saying you have a dozen donuts. That means I have 12 donuts. But I call that group of 12, I call it a dozen. So if I have a gas, there's a whole lot of molecules in a gas, so we say, okay, When we have a group of 6.022 times 10 to the 23rd molecules, we'll call that group 1 mole of the gas. Okay, like I said, just like saying a dozen or a year is 365 days, a month, that's complicated, a week is 7 days. We just give a name to a group of a same thing. And then, so these two equations, these are used when you're given a system. So you have 3 moles of a gas. Oh, another thing you should know is STP, standard temperature and pressure, implies the temperature is 273 Kelvin and the pressure is 1 atmosphere, which of course is 1.01 times 10 to the 5th pascals. So you have 3 moles of a gas at STP. What volume will this gas take up? Well, you would use the ideal gas law. Or maybe you say, I've got a 2-liter container of gas, which is currently at 300 Kelvin. If I know there's 4 moles of this gas in the container, what is the pressure of the gas? These types of things. Here's a system. Here's some information about it. Give me the rest of the information. That's ideal gas law. The second way we could use the ideal gas law is when we make a change to the system. So let's say you have a gas system. Maybe you have a container. Here's the container. And you have a bunch of gas in here. And this gas is at some pressure. It's at some temperature. We know the volume of the container, whatever. But then maybe there's a piston in this container. Right? And so I'm going to push down on the piston, and that's going to compress the gas, making the volume change to a new volume. Then I can say, if I change the volume to this new volume, how does the pressure change? Or how does the temperature change? Or if the temperature is kept constant while I do this, what's the new pressure? The way you handle this type of problem, this is still the ideal gas law. What we do is we say, look, PV equals nRT. If I divide the T over, I have PV over T is nR. Well, R, this is just a number, 8.314. That doesn't change. It's a number. N is how much gas are we talking about? 2 moles, 5 moles, half a mole? What is this? That's not going to change in this system. Right? You put the gas in the container, it's sealed, and now you squeeze it. That doesn't make you lose some gas or gain some gas. It's the same amount of gas. You're just pressurizing it. So this right side, this is a constant. And so if I have some left side with a bunch of characteristics is equal to a constant, and I could change those characteristics, then that implies that PV over T in my first state, in the initial state before I do anything, must be PV over T after I did some stuff in the second state. Kind of like conservation of energy. You have a hill, here's your block at the top of a hill. This guy has 0 kinetic energy, and it's got potential energy, which is mgh, some amount. So the total energy of the system is you add these two numbers together. Then later on, this block has slid down the hill and is now sliding along the ground. In this new state, I have some kinetic, 1/2 mv squared. That's the kinetic. And my potential now is 0. Because I'm not in the air anymore. I have no potential energy. So the total energy of that state is you add these two numbers up. And what conservation of energy says is the total energy never changes. So whatever this number is at the beginning, it better be equal to this number at the end. That's exactly what this is saying. You have these characteristics. You do this relationship, PV equals PV over T. And when you combine them in that fancy way, that number will never change. If you change P to some new P, the other things adjust themselves so that the new P times the new V divided by the new T is still the same number. Now, a lot of times you'll see this as kind of three different rules. You'll see P1 V1 equals P2 V2. And then you'll see P1 over T1 is P2 over T2. And then you'll see V1 over T1 is V2 over T2. All of these, all of this is just that equation. But notice the red equation. If I say I'm going to pressurize this vessel, so I'm going to compress the gas to some new volume. So I got some new V2. What's the new pressure? What's P2? Given I make this isothermal. That is to say, I'm not going to let the temperature change. So maybe I put a little heat sink at the bottom down here to soak up in case this gas starts to heat up as I compress it. That heat sink will pull the energy out so that it doesn't heat up. So in that case, the temperature 1 is the same as temperature 2. So they just cancel out. So this T1 over here and this T2 over here, they're the same T, so this T cancels that T. So you're just left with P1 V1 is P2 V2. And likewise for the blue one. In the blue one, all that says is that the volume didn't change. That's called an isochoric process. And the green one, the pressure doesn't change. That's isobaric. Now, you can have it where all three things change. That's the black equation, the first one I wrote. That's the one I remember. And then for a particular example I'm working, then I know, oh, in this particular case, the volume's not going to change, so I just cancel out the V's. Or in this particular case, the temperature doesn't change, so I cancel out the T's. So don't think of, this is 4 different rules or 4 different equations. It's just one equation where depending on the problem, certain things happen to cancel out and other things don't. But when do you use this? You use this when the system is changing and you want to know about how something else changes because of that. So here's my system, here's some gas, these are the piece of information you happen to know, and then I'm going to change the volume to this new number, or I'm going to heat it up, change the temperature by 200 degrees Celsius. How does the pressure change? Those types of problems, you use this form of the ideal gas law. This form, the normal one you see in textbooks, PV equals nRT, this one is, here's a system of gas, here's some information you know, I want to know the rest of the information. But I'm not changing anything. It just is what it is. It's just sitting there. And I want to investigate it. This one, here's your system of gas, here's some information you know. Now I change something, tell me how the rest of the stuff changes. That's this version. All right, and that's it. So what can you expect for the test? Likely 6 or 7 problems as usual. You've seen my tests before, all calculation based, no definitions or anything. You will have the formula sheet, the same formula sheet that's posted to Canvas right now. I'll print it out with the test. Any constants like Boltzmann's constant, Stefan Boltzmann constant, all these things, they'll be on the front page of the test as well. So all you have to do is practice the homework problems, go over the examples we did in class, and then on Canvas, as I always have, I've got a whole bunch of different practice problems with all my solutions there. Work through these problems yourself. Get a blank sheet of paper. Try working them out. If you know how to work them all out, you're good. You'll find that the test is an easy test. You'll get 100. If you're having trouble with a particular type of problem, then look at my solution, see how I did the first step. How did I start working it? Or try getting, focusing more on those particular examples. Don't waste your time working a bunch of problems on the things you already know how to do very well. Focus on the stuff you're having trouble with. And then, of course, if you have any questions, you're always welcome to email me as usual or come to my office hours. But practice the problems. The problems on the test will look just like the problems on the practice, the posted practice problems or the homework problems. I'm making the test. You've seen how I make homework problems. I'm going to make the test problems the same way. So if you practice them, you do a bunch of examples to where you could just sit with this blank sheet of paper and be able to do it without looking on something else, then you'll be fine for the test. You won't have any issues. All right, so I hope this was helpful, and I wish you luck.